Good afternoon, everyone. Some of you doesn't know me. I'm Chiaki Kobayashi. I'm chairing this session. I'm also working on the chemical evolution of galaxies. So now we have a different type of chemical evolution. You have heard about this molecule formation. That's also chemistry, but Donatella Romano is going to tell us how nucleosynthetic and galactic chemical evolution happens. Actually, Donatella and I met long time ago when both of us are PhD students in a nice conference, and then we still are very good friends, and in the same field, we got a job. So maybe many of you find a good friend now, which may become 20 years later a very good friend. So this is a great opportunity to find a good friend. It's a great pleasure, Donatella, introduce you to this talk, and then please take it away.
Thank you, Chiaki. Very nice words. Thank you so much. So good afternoon, everybody. And this is all about stars and how they enrich the interstellar medium. We heard yesterday in the talk by Javier that there is an interconnection in between interstellar medium and star life cycle. So although I feel a little bit of an outsider here, I hope that this topic will be of some interest for you. May I just ask you, how many of you are familiar with nucleosynthesis, galactic chemical evolution? Just to know if it is completely... Yeah, you can raise your hand. No? Okay, it's not too bad. Okay, so... we make use of galactic chemical evolution models because they allow us to follow the evolution of the chemical composition of matter in galaxies, of the gas, which is taken as one phase in the simplest cases. And I will mainly talk about those. So we can follow how all chemical elements change according to different physical processes and in different galaxies and different galactic components. And the aims of the lecture is to get for you to get acquainted with the ingredients, main assumptions of the models, especially those of you that never heard about that, and also learn about the successes, but also the failures, the shortcomings in reproducing the data that we have for chemical abundances. And also be aware that there are many challenges because chemical evolution is often seen as a closed box. So we take some routine that compute chemical evolution for us, and this is well known, this is easy, but there are many uncertainties in the process. And then I also hope that some of you can inspire it and okay, here I am again, that can be inspiring for your future research. Because indeed for me, when I was asking for my master thesis in physics, I was just going around talking with the professors, and I came across this research field, started reading some papers, even old papers. So people read old papers because there is something interesting in there. And the idea that we can measure chemical abundances, from that we can infer the history of galaxies, for me was so fascinating that I decided to dedicate my studies to this, and I was lucky. My career basically was dedicated to this, and of course is also should also be understood that the field require a quite wide knowledge about different mechanisms that can change the history of chemical evolution of galaxies. So you need data, you need theoretical prescriptions, and you range from atomic physics to processes that happen on the scale of galaxies. And so there are many uncertainties in this, and you can Maybe you heard about galactic archaeology. This is a flourishing field now. Okay. Thanks to large-scale spectroscopic survey, and here I provide a very quick overview in one page. Thanks to Sara Lucatello, my colleague in Padua, that collected all the information from the web. So what we do now is fantastic because in the Milky Way, we can map the chemical composition of stars. Yeah, maybe I turn to that one. Oh, no, it depends. So we can have a detailed picture of the enrichment in stars belonging to different galactic components. And we also have, thanks to Gaia, the information about positions and motions. So we can constrain both stellar evolution and nucleosynthesis and also probe the dynamics. And we can find streams and we can have an idea about the mergers that happened in the past history of the Milky Way. And with information about stellar ages, we have thus the characterization of the full chemical history and assembly history of the Milky Way. So starting from RAVE and SDSS, the information that we could access with this kind of survey, they were designed to cover a large number of stars, was still limited because they provided essentially stellar parameters, radial velocities, and in the case of SDSS, alpha over iron abundances. And then with the Gaia ISO survey, we had high resolution spectra for less stars, but very good high resolution spectra. And so we could access basically all the elements in the major nucleosynthesis channels, alpha, iron peak, neutron capture elements. Come on. And with Apogee, we could do some sanity check because we have abundances from the infrared. So you can compare how a given element behaves with detection in the optical or in the infrared. And then there is Gala and now Lamost and also Gaia. In the DR3 release, we have a spectra for 5 million of nearby unevolved stars on the main sequence, which are not very high resolution, but still very useful, as we will see. And more is coming because it has already been mentioned. We have this WIP survey, we had foremost moons, cubes will be a high resolution spectrograph covering the UV. Resolution will be 7,000 and so we could access in this way essentially many lines of neutron capture elements in metal poor stars. That is a field that is increasingly attracting interest because of the interest we have in the first stars and probably in the early stages of evolution of galaxies. And then there is Andes that will be the high resolution spectrograph for the ELT, to which European community is spending some efforts because it will have a resolution of 100,000 and it will cover basically all the interesting spectral range from the UV, hopefully to the K-band. Now this is under discussion because essentially of the cost. So we are really, by the way, we are really trying to find even more science cases to push to the construction of these K spectrograph. So if you have some good idea, that's more than welcome. Okay, so so many data. So what are the achievements? I have selected, of course, just a few results. And so, sorry, this is the bias of the speaker. Maybe you have your favorite one. But anyway, 10 years ago, these maps appeared and I think it's very nice because the galactic disk is dissected in both the radial and the vertical direction. And in all these panels, you see the behavior of the alpha over iron ratio as a function of the metallicity that can be taken as a proxy for the age, for the time that elapses from the beginning of the formation of the galaxy. And so basically, by just a quick look at this plot, you see that there is a galactic abundance gradient, that there is a galactic abundance gradient that is different according to the height of the galactic plane. And also you see how the thick disk disappear moving to large galactocentric radii. There are no anymore alpha-enhanced stars that usually characterize, at least the bulk of them belong to the thick disk. So this is useful to constrain galactic chemical evolution models and models of formation of our galaxy. So we also have information from open clusters. And these are extremely interesting because you can estimate the ages, while for field stars, the ages are very uncertain. Especially for the giant stars, it is basically impossible to determine the ages from isochrones. We will have now access to ages from asteroseismology. But anyway, for open clusters, you have at your disposal a simple stellar population that were born just in one shot, so same chemical composition, all with well-defined ages. And here you see something weird because, okay, first look at the plot on the left. This is the trend of the metallicity gradient. So the trend of the iron abundance along the galactic disk. And the color code is according to the age of the cluster. So each point is an open cluster. And you would expect naively from models of galactic chemical enrichment that the metallicity increases with increasing time. So as long as the structure evolves, it gets more and more enriched in metals, but it is not true. So you see the red line and the red points, they happen to follow below the green and beige ones that are older. So there is something that push the metallicity towards a different evolutionary tracks. And this is seen also for a variety of chemical elements. You can see here on the right all the elements that have been derived from the Gaia ISO spectra. They are grouped according to their nucleosynthetic origins. And so you see again this behavior that was not expected. And then, of course, other interesting results are those related to the mapping of the streams. You can identify from a dynamical point of view coherent groups of stars that are the remnants of satellites that were accreted by the Milky Way. And you can also characterize these stars. And this is how the Gaia Enceladus merger was discovered. So you first can discriminate the stream, then you can do detailed spectroscopy, and indeed you find that the stars distribute in specific region of the alpha over iron versus iron diagram. And then I think it is also important that doing with these high resolution spectroscopic survey, you don't have access only to information such as iron alpha elements, but also to some peculiar elements that are very interesting by themselves. For instance, lithium. Lithium is a special element because together with hydrogen and helium is the only element that is synthesized in the Big Bang. So you have immediately a connection with the theories of standard Big Bang nucleosynthesis. And what is known actually since a long time is that there is a mismatch in between the abundance of lithium measured in dwarf halo stars, that is called the speed plateau, by the way, is here, this red line, and abundance of lithium in the scale log lithium over hydrogen plus 12. Okay, so this is here. These are all halo stars with similar properties. They are warm, and the green line that you see here are the prediction of the standard BBN theory constrained by Planck data. Okay. So people is still struggling to understand this difference. With some people thinking that are the SBBN predictions to blame, so there is something wrong in the basic physics, and other people thinking that there is something wrong in the physics of the stars, because actually, according to classical stellar evolution models, we do not predict this lithium destruction. So according to those classical models, we should actually see the primordial lithium content in those stars. You know, lithium is very fragile, so when the metallicity increases, instead, the model predicts a different degree of depletion. Lithium is easily destroyed, and this is why here you see this cloud, the data are very scattered. So what the models try to do to explain the evolution of lithium is to reproduce the upper envelope of the data in the hope that those stars are not depleted. And so back to the left panel, there were two recent important results to understand lithium evolution. The first is that indeed support the standard BBN nucleosynthesis, because in the GALA data, they found hint for a warm plateau. So there is not only the speed plateau, but there are hints that here some cold star, some hot star have preserved their primordial lithium. Lithium is easily destroyed in the stellar interior, is very, very sensitive to the physical parameter of the stars, to the temperature, but also rotation and other parameters. So the fact that in this very huge sample of stars, we see a minority of stars defining this plateau is important, because it's telling us that indeed all those stars belonging to the speed plateau have depleted lithium. And if it is true, we must find some mechanism, some extra mixing mechanism in stars to bring all these three group of stars in agreement with a similar, we must have a story that explains everything. And a spoiler, we have now submitted a paper in which indeed it is possible to put all these things in context with specific models for stellar evolution. As far as the evolution, the galactic evolution of lithium is concerned, here you see different models that are the lines compared to the data. So as I said, everything which is below the meteoritic value, that is this yellow cross here, must have destroyed the lithium to some degree, while in meteoritis, the lithium atoms have been locked and they are not exposed to stellar evolution anymore. And so this should be indicative of the level of lithium enrichment that has been reached in the solar neighborhood. What we found, thanks to the Gaia ISO survey and thanks to the high number of open clusters that we survived, is that okay, we can take a number of clusters along the galactic disk. So this is important because in this way we can trace also the gradient, and this was never observed before. We had only local data. And with these open clusters, we also know the age. And so here the clusters are color coded. Brown is for young and yellow is for ancient cluster up to 4 gigayear in age. And so you can discriminate in between different models that adopt different prescriptions for the nova systems that are the sources of lithium in galaxies. So depending on whether you have a minimum mass of one solar mass for stars that enter the building up of these nova progenitor, or only massive stars that enter the building up of nova progenitors, you have very different theoretical predictions for the gradient, and so you can discriminate and you have information about the evolution of the peculiar systems. This is important, I think, because novae produce lithium, as we will see in a while, but also some isotope of carbon, nitrogen, and oxygen that can be also measured in the interstellar medium. So there is a connection in between stellar evolution, interstellar medium, and what we can measure in stars. And then another important achievement, again, as I said, there is no a one-to-one relation in between time and metallicity, even if it is still sometimes seen in the literature. This paper was published by Nepal for his PhD thesis work, and what they did is to take from, they used Gaia spectra, so they have only basic information here, and what they show in the paper is just the metallicity. So they have over 200,000 main sequence and subgiant branch stars. These stars are unevolved, and so they are the stars for which it is more reliable, the estimate of the age. In this way, they could divide the sample of stars in age and metallicity beams. So here you see the tumor diagrams of the stars, where the metallicity, the age is increasing from top to bottom. So here you have the oldest stars, and here the youngest one, and the metallicity is increasing from the left to the right. And so basically you see the striking results that at older ages, you have a coexistence of stars that span the whole metallicity range from very metal poor to super solar rich. And this was something unexpected, that you can find thin disk stars, so in thin disk orbit, so old and so metal rich. And this is something that has to be investigated by the theoretical models. It's something that at the moment we do not explain yet. And then the possibility of coupling the spectroscopic data with asteroseismology that allow you to have very precise ages for stars. This is a recent paper by Pinsonneau. Actually, to me, asteroseismology is kind of black box in the sense that they take the data from apogee spectroscopy, Kepler asteroseismology, and with some magic, they give us really precise measurements of radii, masses of the stars, and thus ages. And this is very competitive with the traditional isochron age estimate method. And so you can do even more precise modeling when the ages are known. Okay, this was for galactic archaeology, where you have all this beautiful survey and you have access to resolved stars. What about extragalactic archaeology? So we already heard a number of lectures on this topic. For extragalactic archaeology, we have at our disposal a lower number of elements. Of course, we cannot access interesting elements such as neutron capture and others. Still, we can measure helium, we can measure CNO abundances, neon, and thanks to NIRSpec on board James WST. We also heard that we must be very careful when we are looking at these chemical abundances, and we want to compare with what we found in the Milky Way, because there may be problems such as the gas density may be misunderestimated, and this can lead to can easily translate your abundances in different regions of the chemical diagnostic diagrams. So the point is, how do we exploit this data? And yeah, we can use galactic chemical evolution. As I said, is not a theory yet, it's a framework where you can interpret what you observe in the gas, in galaxies. And you can use either a code that is standalone code, or you can build a module coupled to more complex cosmological hydrodynamical simulations. In the first case, this is computationally cheaper, of course. This is a big advantage that you can run on your laptop in 5 minutes an entire galaxy. And also, you can follow basically as many elements you wish. You think an element, you can put in the network, and this does not slow down the simulation. On the other hand, if you use cosmological context, full hydrodynamical simulations, you use more HPC resources. You can follow a subset of elements. You must choose which are the elements that you think are more interesting. But of course, you have more physics since they are more solid from the point of view of the physics inside. So, which are the ingredients of chemical evolution models? Of course, you must start from some initial conditions, and of course, the initial conditions are a bubble of gas with a primordial chemical composition that we can take for granted because we know it from the standard Big Bang nucleosynthesis theory. And then we may decide if we want to evolve a galaxy in isolation, if we want to allow for accretion, ejection of matter, if we want to put the galaxy in the cosmological context. And then the star formation rate. The star formation rate, as we already heard, is a big problem because we basically do not know how stars form out of the interstellar medium, out of the molecular clouds. And so what we do is just take some empirical laws that are subgrid recipes in hydrodynamical simulations, and in our case are analytical laws. Usually you assume that the star formation rate is proportional to the density of the gas, the total gas, to the 1.4 power. And an important addition that you can make to your model is using star formation histories that are derived from observations. In fact, for the Milky Way and nearby galaxies where you can resolve stars, you can build color magnitude diagrams. And here you see color magnitude diagrams with observed stars and simulated stars. So you can play this game of assuming a star formation history, running some Monte Carlo in your computer, and you extract the stars in given phases of evolution, and you build your diagram that you compare with the observed one. And you do that until you find a match by changing essentially the star formation rate at each time step of the simulation. You can change the initial mass function of stars. In this way, you infer the star formation rate as a function of time. And here on the left, you can see the inferred star formation rate as a function of time in the thick and thin disk of the Milky Way. These are very recent results by Ruiz Lara and collaborators that have been obtained thanks to Gaia. And because of course, the precise motion of the star, the position of the stars that you can obtain. What you see is something rather unexpected, because the evolution of both disks, although a little bit scaled, show that in the past there was a birth. This is something that we can understand. And then a decline of the star formation rate. But here we don't have secular evolution. We have these very pronounced peaks, especially the one at around 5.5 giga-year ago. And here you have other secondary. There is 1, 2, 3. So someone knows, someone can guess what's going on here. the ones who are not sleeping. Try to guess. How can it be? This is the Milky Way. This is the solar neighborhood. This is the formation history of, the solar vicinity. Everything seemed quite smooth. And then these merger. Merger. Okay, I don't ask more. But I put here this cartoon with Sagittarius, indeed. Is the merger with Sagittarius, and just looking at the results of previous 10 body simulation, you can see that you expect, because you have, you can follow the Sagittarius remnant and the trails, you can build models for the ingestion of Sagittarius. And so there have been three, it is predicted that there have been 3 major collisions between Sagittarius and the Milky Way. And these episodes match well what you see now, the star formation history inferred from the color magnitude diagram. So I think this is pretty much a nice results, because as you can see, most simulation date well before the derivation of the star formation history. Yeah. Passage number, yeah. Yeah, it seems so also for passage 3. What I would say is that they are, okay, the Milky Way disk is built inside out. So you build the idea is that you build the thick disk, forget about perturbation, so on and so forth. And then a larger mass will end up eventually in the thin disk. But this is built gradually. And in this way, here, the mass in thick and thin disk is more comparable than it is here. So this is at least what I have understood that can explain it. So star formation rate, then there is, of course, okay, this is a big problem. I don't know how you pose with this, because until I think 10 years ago, when I went to conferences talking about the possibility that the IMF is varying, people were really, standing up. It is impossible. If you change the IMF in your models, you reproduce everything you wish, so it doesn't make sense at all. That was the usual. But my feeling is that as a researcher, we should explore, right? We put our assumptions are this one. We can discuss, you can agree or not agree. The point is that in many chemical evolution works, I think also Chiaki used, let's say, universal initial mass function. So I'm absolutely fine. This is something on which we do not agree. We have found something. The point is that when you form stars, you assume an initial mass function, and this is derived essentially from, in the best cases, from observation in the solar neighborhood, right? Because what you can do, the most direct method is counting stars, but this is the present day mass function. You have to infer the one at the beginning. There will be correction because the stars are aging, are moving, have binary companions, as we already heard. And all those, and then you also have to assume a star formation history, by the way. Now we have a very good one, but was not the case until a few years ago. So all those corrections must be taken into account. As I said, the IMF that you infer from direct count will anyway be local IMF. There are some indication, and here I just put one possibility in the paper by Cappellari that analyzed early type galaxies and indeed found deviation by looking at the M/L ratio of stars. So there are indications of variations, and I think they are intrinsic. And also there is another point that was already mentioned, that we talk about IMF, but we should talk about IMFs. There are indeed many initial mass functions, because stars form in cluster and they will have a given distribution of initial stellar masses. But then think about you want to compute the chemical evolution of galaxies. So you will have to combine in multiple association clusters. So you will have a composite initial mass function, a cumulative composite if you take into account the history of that specific region and the galaxy wide. And now people are working also on the cosmic initial mass function when you put together galaxies in clusters. And then there is another point that it is not trivial at all, I think. Is the stellar initial mass function an invariant probability density distribution function, or is it an optimally sampled distribution function? What does it mean? So very often when you want to sample the IMF, you take a given shape and you pick up stars randomly. Is someone else doing something different among the one who do this exercise? No. So that means if you assume that for the stellar IMF, that means that two clusters that are born with exactly the same mass, exactly same metallicity, density, same environmental condition, will have different stellar initial mass function, right? You just do the exercise and randomly pick. In the case of optimal sampled distribution function, the assumption that is made is that two clusters that are born with the same chemical, the same physical properties will have the same initial mass function. And this will lead to differences where you want to sum up all the cluster IMF, the galaxy wide IMF, and so on and so forth. So myself, I'm still using the invariant probability density distribution function, but I think that this idea of an optimally sampled distribution function should be investigated more. Okay, then yes, another ingredient to enter the model is the gas accretion, and of course you can either assume some analytical law, or you can take results from dynamical studies, for instance, the inside-out formation of the galactic disks. So assume the timescale of formation is longer in the outskirts of disk. You can take merger history from cosmological simulations. So do whatever you prefer. Then there are the gas outflows, and here we have already listened, is a huge problem. Is a huge problem because, for instance, for some low mass stars, there are deviations from expectations in the sense that you have shallow potential wells, but some galaxies manage to get rid of their metals, while others seems want to keep the matter within them. I think that we have very advanced hydrodynamical simulation that are taking the outflow. But again, what I would like to see, for instance, is the dependence on the IMF, of assuming different ejection energies for different supernovae. I think this is a field in which we really need much more work. This could lead us to understand the variety of situations that are seen in reality. Okay, then about gas flows, you can have also galactic fountains. If the potential well is strong enough, supernova ejecta can just move a little bit above the plane and then recollapse again. And has been proven that from the point of view of chemical and galactic fountains are just slightly delaying the enrichment. The effect is negligible, while radial gas flows are important. These are the flows that you expect when you have inflow of gas. And since many models have this inflow you must also take into account radial gas flows. Then there is the core of chemical evolution models. This is stellar evolution and nucleosynthesis. In one slide, stellar evolution, I think that you all saw stellar evolution in your university courses. What we need to know to understand the following plot is just remember that low mass stars have long lifetimes. They take a lot to burn hydrogen in their core on the main sequence, and then they have a quite complex evolution after the main sequence, while massive stars, here on the right, have a very fast evolution, many more nuclear burning, and then they up with this onion structure. You have the passage of a shock wave, you synthesize with explosive nucleosynthesis the most heavy elements. Okay, and so, sorry, the other way. Okay. And so in the end, what matters for chemical evolution is which sources synthesize which element. So massive stars produce mainly alpha elements, but also some are processed depending on which kind of massive stars they are. On very short time scales when they are treated as single stars, or if you couple in a binary, you have longer time scale. So you can have neutron star mergers, maybe black hole neutron star mergers that will produce a process element on long time scale. Process elements also coming on short time scales from collapsar, magnetar, this kind of more exotic objects. Then you have AGB stars, low mass stars that mostly produce carbon, nitrogen as process elements on much longer time scale that can vary from 30 mega-year to a Hubble time. And if the stars is in a binary system, you have type 1a supernovae, novae, and these produce different kind of elements. In particular, novae are important for producing some rare isotopes. And so this is a very schematic view about the origin of the elements. So just in one slide, you see for Big Bang nucleosynthesis, you have hydrogen, deuterium, helium-3, helium-4, and the isotopes of lithium. Well, don't forget that we always say that heavier elements are produced by stars. Actually, there is also cosmic ray spallation processes that produce lithium, beryllium, boron. And then single low and intermediate mass stars. And here you have the isotopes that they eject into the interstellar medium. If they happen to be in binaries, they can lead to novae or type 1a supernovae, and you see that the metal production is quite different. And then you have a very small range of electron capture supernovae, but this basically from the point of view of chemical evolution have no effect. They are, I mean, the range, the initial mass range is so small that you cannot see a seizable effect. Massive stars and the compact binary mergers that are responsible for a huge fraction of the R process elements. Okay, I think we can skip the simple model is not used anymore. The basic equations of chemical evolution. So you set up some integral differential equations to describe how this is the surface abundance of a given generic element. This is the abundance by mass of that element, the star formation rate, the return rate from dying stars, the rate of gas inflow, the rate of gas outflow. We will quickly see all of those. And you can add more complexity by adding motions of gas. As I said, galactic fountains, you can consider radial motion, also radial migration of the stars. Or you can consider a corona, a not corona, around the galaxy. And also, these are homogeneous models where all the ejecta are mixed homogeneously over the volume of the simulation, but you can also add inhomogeneities. Okay, and so you follow the chemical composition due to all these processes. So in the pure chemical evolution models with no coupling with an hydrocode, the star formation rate, as I said, is parameterized. The dependence on the gas mass is determined empirically, and then you have this big parameter that is the efficiency with which the gas is converted into stars. And what is found usually is that for ultra-faint dwarfs, you have very low efficiency, while for bulges of spirals, massive ellipticals, the efficiency could be as high as 50%. And this is just by comparing the observed abundances, okay? So you just try to fit what you see in the chemical abundance diagnostic planes. The infall, many people assume an exponentially decreasing law for the infall. So you have some infalling gas, usually with primordial chemical abundance, but could be also enriched. Here I put a simple form, just one single exponential, but you can consider different episodes if you want to model, for instance, interaction with the satellite or multiple mergers. And then there is the galactic outflow that I think after stellar nucleosynthesis, after the choice of the IMF, is the third major source of uncertainty in this kind of models. What we do usually is to take away fraction of the gas when the binding energy of the gas due to supernova explosion exceed when the thermal energy of the gas exceeds the binding energy that you compute assuming a dark matter halo mass. So the return fraction is given by the sum of different contributions. So different kind of stars that evolve in isolation. So they provide their ejecta at the right time with the right time delay, which is important to treat correctly the enrichment of the different elements. And you also have different binaries, which are not all the possible binaries that you can have, because of course, for instance, massive stars that are interacting on the main sequence are not considered in this kind of computations. Okay. And so here is just for one of these terms, the form that it takes, you integrate over the relative stellar mass range, the yields, considering the stellar lifetimes, and the shape, the chosen shape of the stellar IMF. Okay, the stellar yields. So here you read essentially grid of yields that are produced by people computing stellar evolution and nucleosynthesis. And so this is another source of uncertainty. So the mass that is ejected in form of a new element by the star will be computed as the sum of mass ejected through winds and mass ejected through supernova explosions. So for instance, if you are looking at low mass stars, you don't have this term, of course, because the star does not explode. And then you have to consider also the mass that was present in the star at birth and didn't go through any nuclear reaction rate. So this one also is ejected. Remember that this newly ejected mass may actually be a negative term that subtracts a fraction of that specific element from the computation, because stars not only produce elements, but also destroy them in their interiors. And so the stellar yields table are something like that. People compute the mass of elements, of different elements that are ejected as a function of density and stellar mass. And of course, these are discrete grids, so the problem arises that you have to interpret and sometimes also extrapolate to cover the whole range of stellar masses. This is, by the way, is one of the finest grid for low and intermediate mass stars that is available in the literature. So the takeaway message is the major uncertainty when you want to compute galactic chemical evolution are the stellar yields. Even if you run a complex hydrodynamical simulation, if someone asks you which yields are you using, you should be able to answer. Otherwise, I cannot understand the kind of match you have in between your model predictions and observations. Main problems related to the stellar yields, the poorly known nuclear reaction rates, and especially one of the most important ones which determines all the nuclear burning post-oxygen. So it's very important for nucleosynthesis from massive stars and also for the mass of the remnants. Convection is still not well understood. And you often, in order to explain the observation, have to add extra mixing, and these are different physical mechanisms that may be rotation, that has already been mentioned several times, but also thermal in mixing, and then there are the magnetic field. And a big problem that sometimes is not realized is that there is a coupling in between all of them. In many models, there is just a treatment of 1, 2 in addition to convection. Adding everything together is never been attempted, so who knows? Mass loss rates. I show you before the formulation of the stellar yields. And that formulation, there is a continuous rate of mass loss from the star, but we know that the stars are not losing mass continuously. They have bursts. Then they have phases in which they do not eject the matter. So if the surface composition of the stars changes in correspondence of those phases, the true yields will be different from the one that are calculated. The mass cut location in models of massive stars is another big uncertain quantity. And as I said already, possible binary interactions, and the fact that in order to produce these grids that are useful for us, we need many models, and people use 1D model for the star, while stars are 3D objects. And this is another very big problem. I will just spend a few words at the end of my lecture. So galactic chemical evolution models are useful for a number of topics. We basically can establish a chronology of events, infer how the system was formed, have information on the galaxy-wide IMF. This is the classical diagram, alpha over iron as a function of iron, adapted from work done long ago, showing you that according to the type of galaxy or galaxy component we are considering, the predicted evolution is very different. Of course, the predicted evolution when compared to the data matches very well. And what affect mainly these curves is the star formation rate. Lower star formation rates move the curve toward lower metallicity. Higher star formation rate move it toward higher metallicity. The IMF shift in the vertical direction, and outflow can change very much the slope of the curve. So you see immediately in this diagnostic diagram the effect of different physical processes. There are many other diagnostic diagrams. If you are interested in one particular, come to me and we can discuss. And then, yes, the other point, you can constrain stellar evolution nucleosynthesis theory in a statistical way by comparing the predictions that you get, changing the model parameters to set of abundances. And as I said, now we have really a lot of stars, especially for the Milky Way. And I think I can stop here for questions if you have doubts about this part.
I count myself as a student of
I am a student in ISM and magnetic fields, so that's...
So I had a question about lithium. You said that lithium is quite sensitive and is easily destroyed in the stars, but is very well maintained in the meteorites. And I wanted to understand a bit why. How come? Because meteorites can be also remelted, and yeah, so how come this is...
Yeah, what I mean, it is basically, it is locked into the meteorites, and then there are no nuclear reactions. When I say that it is easily destroyed, it is destroyed at temperature slightly lower than 10 to the 6 Kelvin. So it is always, I mean, sorry, I understand maybe the audience is not used to these. In stars, you reach temperature sufficient for nuclear burning, so it is another energy and temperature regime. So that's the point.
Any other questions? I think basic questions are also very much welcome now at this stage. Everything is clear?
I can go on.
Yeah, there is one more. Go.
Can you tell me a little more about how the IMF could vary, not just on the metallicity and the population, but other factors maybe?
So you mean what I can expect can
Yes.
drive the variation of the IMF? This is the question of 1,000,000 and another million of dollar, euros, whatever you want, that I don't have, by the way. The point is that, as I said, we don't have a grasp of the physics of star formation. I can show you some further plots. What we are trying to do is try to understand the origin of the stellar initial mass function by looking at the core mass function. And in doing that, I'm thinking about the ALMA IMF survey. We see that we can add information with respect to local molecular clouds. So we have different condition, density, metallicity, and so on and so forth. And there, the core mass function is indeed biased to massive stars. So you can look toward the galactic center. I don't know if this was your question.
Yes, so I wanted to know, like, if there is a variability with respect to the dynamics in the ISM and such.
I don't know if there are detailed studies, but yeah,
Okay,
there are studies of star formation. I'm thinking about the simulation by Mike Grudich, this stuff. I don't think that we can say now if there is a clear correlation in between the many,
Okay.
you know, the
Okay.
many unknown.
Thank you.
A very short one. I have a very quick question. On the list of uncertainties, there was a point, possible binary interactions. Does this concern tidal forces or an exchange of matter?
No. So this is interactions. This is about the fact that we know that many stars are in binary systems, especially if they are massive. And if you noticed, when I was showing the origin of the elements, I was just showing single stars or binaries in which the stars are low mass stars. This is because actually there is, to the best of my knowledge, one team that is studying the chemical yields of interacting massive binaries, and they do not have a grid that is useful for chemical evolution.
Okay, any more questions? All clear? Just one comment on the IMF. There are simulations on ISM and including turbulence, magnetic field changing chemical composition, and people trying to predict IMF as well. I think there is some effort as well. Okay.
Okay, so let's move on. As I said, the yields are uncertain, but there are also some things that we understand very well by now. And in particular, I think one can be very interesting for the topics covered in this school. Now we know that stellar rotation is responsible for the synthesis of huge amounts of primary nitrogen-14 at low metallicities. This is something that was investigated back in 1973 by Chris Neden in his PhD thesis. He measured the nitrogen abundance in dwarf halo stars, finding this plateau rather than the expected decrease with decreasing metallicity if nitrogen would be secondary as expected by normal stellar nucleosynthesis. With rotation, you can boost the mixing and you can give some carbon-12 seed in order for the star to produce lot of nitrogen-14 out of the CNO cycle, even if they are metal poor. And by the way, stellar rotation is very effective at low metallicity, and then the effectiveness decreases. And then for the ones that can be interested in damped Lyman alpha systems, zinc can be an interesting element. And in order to reproduce the observations in halo stars, so low metallicity ambience, we need hypernovae, so explosion more energetic than normally assumed. And there are some elements that remain very critical that we still do not understand. That maybe there is something wrong in the nuclear reaction rates that we always blame, or we must understand better maybe peculiar type of explosions. So at this point, I will quickly go through a selection of results because till now we have just a recap of stellar evolution of the ingredients of chemical evolution models, but so what you can do with these models. So actually here, a model that has been quite successful is the twin-fold model for the Milky Way, in which you form the thick disk out of one infold episode on very short time scales, and then you build up gradually the thin disk. Of course, this is, you know, valid for the large scale average behavior of the abundances, doesn't hold if you want to look some very peculiar small scale environment. So in the plot, you see the trend of alpha over iron as a function of iron for apogee stars. And the predictions of a galactic chemical evolution model are shown as the line, and you see also some specific time. So this is basically the age with which a star will form once it is here, about 13 giga-year, and then here at 9.4 giga-year of age, the thick disk formation is stopped. You accrete new fuel for star formation, so the curve move toward lower metallicity because the accreted gas is metal poor, so dilutes the metallicity of the medium. Then you start forming stars again. You try to restore the alpha over iron ratio typical of massive stars. Then low mass stars die, and supernovae type 1a produce iron, and you have this kind of ribbon that reproduces well what you see in the observations. So even with a very simple, quick model, you can explain what's going on. And an important observational constraint is the distribution of stars as a function of the age. As I said, we use the distribution of stars as a function of metallicity. Ages are much better because metallicity can be not so tightly related to time because of local inhomogeneities, for instance. And so here you see the behavior of the model, the light blue histogram, and the data for the thick disk and thin disk, or I should better say high alpha stars and low alpha stars. It is pretty good. Apart from some clear deviation. For instance, here you have a tail of young stars, young thick disk stars that are not predicted by the model, and also for the thin disk you have a few very ancient stars that the model cannot explain. You can do this exercise not only for magnesium, you can check different elements. It's a useful sanity check. So I usually do not trust very much models showing just one element. It is good to show many more and see that there is a consistency in between model predictions and results also for other elements. Here you see each a dot is a star. The stars are divided according to the different galactic components. So in particular here it is nice that the curve for the thick disk can reproduce these red stars here that are I alpha over iron thick disk stars. Recently, by analyzing data from Gaia spectroscopy, it has been found that maybe we need a third info episode, which I think is very nice because we observe young massive stars that are more metal poor with respect to older stars. But if you remember the plot with the star formation history coming from the detailed color magnitude diagram obtained with Gaia photometry, this is exactly what should be, right? Because you have these 3 reignition of star formation. And so in this work by Emanuele Spitoni, he took exactly the star formation history obtained by Ruiz Lara, and with this he was able to explain the presence of these young and metal poor stars in the solar vicinity. A problem that I mentioned here, that you have these stars that you cannot explain. This is because you must account for radial migration. In particular, in the solar neighborhood, you observe a percentage of stars that were not born here. They have migrated. And in particular, you observe stars migrating from the inner toward the outer disk. This will be more ancient with respect to stars of similar metallicity that were born in the local disk, and they will be more alpha over iron rich. And these are results by Ivan Minchev that are confirmed by another N-body simulations by Fiorenzo Vincenzo and Chiaki. In particular, here I think it is even better for visualization purposes because you have on the y-axis you have the birth radius of the star, and on the y-axis you have the radius at which it is found now. And if the stars were just in circular orbits, not moving, I mean not moving in the radial direction, you should observe all of them here on this one-to-one relation, and instead you have this deviation. Clearly, stars born in the inner galaxy move outward. So when you compare the results of chemical evolution models, you must also consider that the fraction of stars has migrated, so they should be compared to the chemical evolution models for the proper birth radius. And stars age. And this is clearly seen in the case of lithium, that is very fragile, easily destroyed in stars. So you can hope to see the original lithium in stars if they are young enough, hot enough. And this is seen in this plot of the radial gradient. Each point is 1 star. This is the current location along the disk. And you clearly see that the ancient stars, the easiest, they are found at low lithium abundance value. Only a few lie on the line showing the prediction of the chemical evolution model for the lithium enrichment. In particular, these with the error bars are open cluster, all the other are field stars. Only the youngest one can be explained. And here again, the cross is the meteoritic value unchanged by evolution processes. Okay, so as I said, inside-out formation of the disk is not enough to explain the abundance gradients. So you must add something more. And people add radial gas flow. And here you see the evolution of the radial abundance gradient of magnesium in the galaxy, predicted with a model that does not include neither of these processes. Here is addition of radial gas flows with different velocities, and here is the addition of variable star formation efficiency. Again, this is an exercise because we actually do not know exactly how the star formation efficiency varies across the disk. If it varies, it is not considered here. There could be also an effect of the IMF. As I said, IMF is finding more massive stars looking toward the bulge of the galaxy. So maybe if the conversion from the core mass function to the initial mass function holds, maybe we should also change the IMF. Okay, and so now something that would be more interesting for the audience. Chemical evolution models can be compared to abundances measured in the interstellar medium from molecular cloud data. And for us, it's very interesting to look into those data because for some elements, we don't have information in stars. We can measure the main isotope of nitrogen in stars, but we have no access to the secondary isotopes. And the secondary isotopes is interesting because it is synthesized in nova systems. And this is basically the only channel through which stars can synthesize nitrogen-15. What you see here are observations of, inferred nitrogen isotopic ratio from a set of molecules. You see that there is a large dispersion, and the line are the prediction of homogeneous chemical evolution models. And with Laura Colzi, who is the first author of the paper, we now want to investigate better the dispersion, because by sure will be partly driven by inhomogeneities in the chemical evolution models that are not accounted here, because I took just an average nitrogen-15 production from novae, partly by other processes that can be fractionation. And so I think these deserve further investigation, and to me is quite an exciting project. So that was for nitrogen. Moving to carbon, also carbon has a lot of problems because if we look at different molecules, we have different estimates of the gradient. And you see, especially in the outer galaxy, it is where these gradients diverge more. And this is very bad because the metallicity in the disk decreases moving toward the outer galaxy. So here we are probing low metallicity regime. We are interested in for studying the early phases of galaxy formation. And so it would be great to have a true determination, something that we can interpret with the chemical evolution models. Okay, so the model agree with the Milan 2005 gradient. There are also studies about the sulfur abundance gradient by my PhD student, Yipeng Zhou. He just submitted, actually, we received already a report a few days ago that is positive, so I hope that he could put soon on the archive the paper. And in orange, you see the predictions of the chemical evolution models compared to the data. Again, there is the huge dispersion. And again, you see that by looking at different molecules, it seems that you have this shift in the observed gradient. That is something that we would like to understand better. Why to look at these strange isotopes? In some cases, they are very useful to infer in. For instance, they integrated the galaxy-wide initial mass function. We had this sample of sub-millimeter galaxies observed at cosmic noon, and it turned out that the 13C/18O ratio is very low, 1 for basically all of them. You see the data are these red points, and you see also the comparison with the local galaxies. They span large range of values. For the Milky Way, we expect ratio around 10 or even slightly lower. So what's going on here? The interpretation that we could give after running a set of chemical evolution models is that the only solution is having a galaxy-wide IMF skewed toward more massive stars. So you have these starburst that create 10 to the 11 solar masses of stars. And in this huge starburst, you produce more massive stars. Massive stars are basically the only producers of oxygen-18. low mass stars just destroy it. And so if you have more, you have a lower certain C/O ratio. And also others are following on this line of using chemical abundance ratio to infer the initial mass function in galaxies. A few words about stochastic enrichment. Again, this is, of course, this can be done with hydrodynamical computations that, however, are very expensive, so you must justify very well why you want to use that. You can also implement in galactic chemical evolution models some stochasticity. And this has been done by my postdoc, Martina Rossi, specifically to study CNO evolution. There are other dealing with the neutron capture elements. So Martina studied the dispersion of C/O and N/O ratio in the halo of the Milky Way. If you look at the data, when you look at these metal poor stars, it is very difficult to have good data because you have a lot of giant stars for which you can perform the abundance determination. But in giants, of course, you have mixing, so the C and O are not any more representative of the abundances at birth. And so we selected a sample of subgiant branch stars. These were carefully selected so that they are well below the red giant bump and they haven't suffered mixing yet, or hopefully just a little bit. So the abundances should be not too much skewed and they should be really representative of the original abundances. So all the data points are newly derived abundances in a homogeneous way, because the other problem is that often you have to put together many different sources, and so the abundances are not homogeneous. So you may have systematic differences, and so you may underestimate or overestimate the scatter. So the point is, can we reproduce the scatter? The gray lines are the prediction of homogeneous chemical evolution models that of course cannot. So you add the population 3 stars, a first generation of stars. These are not exotic objects. They have mass in between 10 and 100 solar masses, so nothing, we do not require pair instability supernovae or 8,000 solar mass stars there. And we take the yields from a grid of Egger and Boozley that is very interesting because, among other things, they compute models with different explosion energies. And you see that when you change the explosion energy, you can cover different regions of the diagram. So this is in yellow, the map of enrichment coming from faint supernovae. Classical core collapse is in orange, then you have high energy and hypernovae. And you see that in this way, while with only one kind of supernova, you would explain part of the observation, but not all of them. By changing the energy, you cover actually the whole diagram. And this is for carbon and this is for nitrogen. So I don't pretend this is the explanation, but it is a possibility. And after calibrating the model on the halo of the Milky Way, of course, we wanted to look at these extreme nitrogen emitters at high redshift. And of course, GN minus Z11 is the most obvious we wanted to look at. Because here you have also some estimate of the star formation rate, that is the red line with the uncertainty region as shaded area. The star formation history of the model is in gray. And here are the predictions, but only for faint supernovae, because faint supernovae are the ones that can produce more, produce higher nitrogen over oxygen ratio. And so here you see the color coding according to the age, the time elapsed since the beginning of the simulation. And here the color coding refer to the mass of the specific faint supernova. So what we have in these inhomogeneous models is different clumps that are enriched by one supernova at a time. Of course, if you want 2, 3 of them, is just you have to average in between the different curves. And you see that it is possible to explain those high nitrogen over oxygen ratio in GNZ11, but you have a specific mass range that seems to be able to reproduce the ratio with the constraints given by the star formation history. And apparently you should have stars in the range 60 to 80 solar masses. So this is just adding up to a series of works that appeared since the measurement of this anomalous nitrogen. And all of those offer different interpretations. So some invoke very massive stars, some invoke first stars, or the model by Chiaki have this double burst star formation history. And recently, there is another paper by Rizzuti that work with outflows, so they can reproduce the ratio, playing with the galactic outflow. So, okay, I was thinking that I was running late, and instead it seems that I'm absolutely fine. I've added just a couple of topic thinking that I think can be related to the topic of the school, so the ISM. I showed you that we rely on the carbon isotopic ratio measured in molecular clouds to constrain our stellar and evolution and nucleosynthesis models as far as 13C is concerned. And this is because here you can see the measurements that we have in stars. So in stars, actually, we can measure the carbon isotopic ratio, but mainly in giants, where you see the effect of stellar evolution. If you want to trace the evolution in time of this abundance ratio, you should look at unevolved stars, and it is very difficult to measure the ratio in unevolved stars. And actually, the measurements are concentrating in a very, very small range of metallicity. All these points that you see here are color-coded according to their age and are solar twins. So basically, they cluster around the sun. You have some measurements for brown dwarfs, for L dwarfs, M dwarfs, but you see, you basically cannot constrain the evolution of the ratio at low metallicity. Is just one star, the Methuselah star. The abundance was derived by Spit and collaborators 4 years ago, but that's all. And for the oxygen isotopic ratio, it is even worse. You have a few stars now, some brown dwarf, some N dwarf are adding, mainly here at very high metallicity. And I think it should be important to look in this problem and to have measurements also for stars in this low metallicity range to compare with what you can observe in the gas, but also in other galaxies. And then I mentioned all the uncertainties in stellar evolution modeling. Something that is really make me think that we should probably revisit the stellar nucleosynthesis we are using is this problem of shell mergers in the late evolutionary phases of massive stars because full 3D hydrodynamical simulations now can treat these mergers. They were already seen in 1D, but now they found an even higher efficiency of convection. So there is room for many more studies. Of course, the problem is that they can just follow a very short evolutive phase up to now. But I think these are some promising direction to better understand CNO and their role also for probing the high redshift universe. And I think that is.
Any kind of questions? If there is questions, please raise your hand. Yes, in the middle.
Thank you for the interesting talk. I have a small question about the in the histogram where you talked about the comparison between thick disk and thin disk. Could you please talk more about the planet migration, the star migration, sorry? Yes, this one.
Yes, in fact, here we know that there is some migration, and what we expect actually is to see a fraction of old metal-rich stars migrating from the inner galaxy to the solar neighborhood. We shouldn't have many low metallicity stars migrated into the solar neighborhood. Here, this is not corrected for the effect of migration. So you see here you have some differences in the histogram. And yeah, when they published the paper, they were mainly concerned on the effect of well-determined ages, but you can correct this. I would say the effect is not dramatic, but of course it should be taken into account.
So it make the differences less drastic than they are here.
Sorry, which differences?
Between like the blue one and the green one, let's say.
Here?
Yeah.
Yeah, I mean, you know, the model is not fine-tuned. This is a first point. It is, I mean, it is more fine-tuned on the chemical abundances. And here the model includes some, takes into account the uncertainties in the ages, takes into account the uncertainties for doing this plot. It takes into account the uncertainties in the chemical abundances, but there is no, I mean, there is no kind of post-processing for dynamics involving the stars. So, I mean, for me, it is okay that there is not the perfect match.
Thank you.
So this data errors are the error of age estimates right here.
Yeah, is these the age estimates are from the paper by Silva Aguirre, is the APOCASC.
And I think he wants to confirm, even with taking into account of these errors, still do you see the migration effect in this?
Oh yeah, yeah, maybe. Yeah. That's I mean the difference is there, is clear.
Good, clear. I think, yeah.
So it's a more general questions because I'm very interested in depletions, elemental depletions. And to estimate those, you have to have a good guess about the absolute abundance on the SM, so not only what you see in the gas phase. And I wanted to know, how do you think, how accurate are the abundance patterns that people assume, you know, for example, by taking the sun and correcting it, and are there some specific elements that you think are quite uncertain?
Yeah, for instance, in my opinion, we have a very good grasp of the evolution of oxygen, something that you could be interested in, because it is quite easy to match observation with model predictions. For carbon, it is less well understood. Nitrogen, we understand very well. I think also sulfur, if you may be interested in sulfur. And another point is deuterium, because deuterium, actually, I didn't show anything about deuterium because we usually don't show, but is the best known element in chemical evolution because deuterium is not synthesized in stars, just enters star formation, and all the matter that is restored to the interstellar medium is depleted in the stellar sense. And so that one would be an excellent element. And indeed, back in 2007, we did with Gary Steigman. He was similarly interested in depletion, and I can show you later the paper. We did a study of deuterium over hydrogen as a function of oxygen over hydrogen by looking at data from the fused satellite in the ultraviolet and comparing with my model at the time. And so you could see the relation in between the depletion, and I think this could be a way to infer the depletion. So I think there is room for work, maybe by a PhD student. And indeed, yeah, there are many things that one could do.
Yeah.
You said that you were comparing the ratio of carbon 12 over carbon 13 to molecules, abundances. Is that correct?
The ratio of carbons.
Yeah.
Okay, so you mean in the gas, or you wanted to
In the gas?
In the gas, yeah. So this, okay, in particular, this work has been done by actually a master student. He looked at the satellite lines of CN, quindi the isotopologues, 12CN, 13CN, and he derived from those optically thin line, the ratio that you see on this compared here. On the right, in particular, they wanted to add some data in this low metallicity regime. And here they have taken literature and they say there are some corrections in the sense that he analyzed some assumptions that are made in literature, the filling factor of 1, Rayleigh Jeans approximation, and he also did correction for the CMB. But I mean, this is not, I haven't delved into the data. So I was just interested in this, you know, incredible scatter and all these difference that you find when looking at different molecules.
Yes, but so I wanted to comment on the scatter in chemistry.
Mm-hmm.
Fractionation reactions that can enrich the molecules, and this has nothing to do with elemental abundance.
Yeah. So
and this could explain, well, I don't know which molecules, but it could explain in some sense, in some.
Yeah. So I know that you can have these selective dissociation, fractionation, so on and so forth. And honestly, I would be very grateful if someone can do kind of computation and put all the outputs from these different molecules, hopefully on a well-behaved relation, and if not, at least understand in this way the origin of the scatter. There is another point. This is something that we actually are working on for the nitrogen isotopic ratio with Laura Colzi. The point is that both nitrogen 15 and carbon 13, they have a huge production from novae. Novae are rare systems. This means that they are enrichment must be stochastic by nature, because you have one here, one there, and one there. And also, people that compute the nucleosynthesis in the nova outburst, according to different initial conditions for the outburst, they find dramatically different yields, in the sense that they vary by orders of magnitude. So it is not surprising to me. I am computing the homogeneous model, but as I showed, we started introducing these inhomogeneities. And for novae, I expect from a theoretical point of view, a scatter that I would like to constrain with the observation. So in my view, should be a work done by both observer and theoretician, because the uncertainties are so large. And I think that we both would gain in understanding something from this process.
Could you also comment on the difference compared to the solar value here? Solar value is much higher carbon 12 to 13 ratio compared to with the other molecules.
Yeah, thank you for the question. So here the solar value is 4.5 about giga-year ago. And the other values are measured in the ISM, so now. And so there are these 4.5 giga-year of evolution in which novae can restore a lot of carbon-13, but also AGB stars, low mass stars that produce in any case carbon-13. So this is the reason why you have the solar value up there and all the local data, local means at the present time sitting there. So you have to compare the same radius. This gives you an information about the evolution.
Great.
I just wanted to make a comment also in relation to what Jerome was saying. So we did do, although we did it for extragalactic environment, we did do models including fractionation to see whether we could explain the differences in 12C to 13C for the different molecules. And what we found was that at least for CO, the differences are not due to fractionation in the interstellar medium, at least not for CO. So although we didn't do it for the outer galaxy yet, and I think indeed Laura is at least looking at the nitrogen one, for CO it seems like it's more of a nucleosynthesis.
So it's more, I mean,
Yeah.
that's in a sense it's good news, but because from the point of view of theory, some scatter must be there, and so I could start from CO to obtain the scatter in the carbon isotopic ratio and then backward look at nitrogen. So it's perfectly fine if there is an agreement that is not fractionation.
Yes, over there.
Yeah, maybe we are on the same line and about the same subject, but what are the different conditions of the where it is really observed? I mean, this ratio, does it correspond to the same densities?
Yeah, sure.
Are there other things than just?
Yeah, I don't have the number, the densities on top of my mind. I can tell you something about the metallicity because that, I mean, it's easy. In the center, you have metallicities above solar, not too much, but let's say from 4 up to 8, you are in a slightly solar metallicity regime. And when you are moving in the outer disk direction, the metallicity is lower and lower. And here at about 14, 15 is kind of Magellanic clouds, okay? In between small and large.
Okay, thank you.
Okay. To students, it's useful to note this carbon-13 behaves similar to nitrogen. It's kind of a primary, kind of secondary process. It's enhanced metallicity or AGB or novae, Donatella mentioned. So you can think the similar figure for oxygen to nitrogen ratio as well.
So here you're showing as a function of radius. Well, it's molecules, but in general, in the plot you're showing the elemental abundance are with respect to radius, and with respect to the position in the disk. Are there variations?
Yeah, I haven't looked into that because there are not so many data points. So, yeah, but I will check. I do not expect very large variation with respect to the position. But yeah, it's a good idea to look if there is a correlation in between the direction you are looking at the ratio.
No, it does not like me. My question is slightly more generic than this. How long does it take to mix the enrichment?
Yeah, so in this kind of models, the mixing is instantaneous. So you don't have a delay. You consider that the mixing time scale because you divide the disk in different annuli, concentric annuli, 2 kpc wide. What you assume is that the mixing is much quicker than the typical time scale of chemical enrichment that are from 3 million years for the most massive stars up to a Hubble time for the low mass ones, if this was.
And so the mixing, in one annuli,
is uniform. I mean, you choose your zone and is uniform in that zone.
But there is no, for instance, a relation between the position of the spiral arms and the enrichment?
No, everything is mixed up. Yeah, you don't, I mean, this is not an n-body and you are following the star or the star particles. So it's just a numerical model, but relying on the kind of equation that I showed you. So, I mean, you do not resolve small zones. You have these concentric annulus and everything is mixed. So this is why even if you want to look in different directions, my model cannot explain any systematic trend if it's there. But yeah, one can check.
It's related to the time history, the cosmic history of enrichment. If you're taking the population 3 stars, they will enrich a lot the medium very quickly, or do we know this?
Yeah, absolutely. I don't want to show here the picture for the carbon isotopic ratio because it's ending up in a paper that is work in progress. Yeah, it is very interesting because actually if you take into account a single generation of population 3 stars that explode in different clumps can be there in situ, can be accreted from dwarf stars. You see that basically you can cover the whole low metallicity range. So this is from, I think the usual iron over hydrogen is about from -0.5 up to the lowest ratio. So really they help you to have a large dishomogeneity. So we can also explain other, I mean, in this framework, you can accommodate other problems that you have with the homogeneous models. So now we're showing these elements because are maybe more interesting for people doing ISM studies.
So your equation of chemical evolution was function of time and radius only. So that was the, I think, confusion, causing confusion. And here, it's the opposite extreme, right? Mixing is very inefficient, so that the stars can be formed. If stars are formed directly from supernova ejecta, they can have very high metallicity. And that kind of inhomogeneity is forced in this series of models, if I understood correctly.
Yeah, absolutely. You don't have any dynamics in, so you just assume the clumps are there.
Any other questions from students? One more time, can you go back to the alpha to ion diagram? That's the very important diagram to students. And can you explain the track again, why you have this? Maybe go back to the Spitoni figure. Yeah, what causes this track?
Yeah, so, okay. Here it is a simplified model. So you have 2 infold framework. You have the formation of the thick disk inner halo out of a first infold, and then a second one. So in the first infold, you have basically primordial gas there. You ignite star formation very efficiently. So you form very quickly the stars. They have the typical alpha over iron ratio of massive stars. And there is this decrease, please look also at the scale. There is the decrease due to the appearance of the first type 1a supernovae. So it's not so steep in other plots, but just because of the scale. And then you consume the gas. At this point, you have another episode of gas infall, and this will be gas collected from the circumgalactic medium, or in our model, we don't have cosmological context. So, but anyway, it will be metal poor gas, and so your metallicity will decrease. And when you have enough gas, you can reignite star formation, and so you try to restore to the alpha over iron value typical of massive star ejecta, and then you have both the type 1a supernovae from the previous star formation episode and the new ones, and so you see this very steep decreasing trend again. And I mean, you can add other infall episodes. If, for instance, if you take from cosmological simulation the history of accretion, you can do this chemical post-processing and have even more complex behavior.
So alpha elements such as oxygen, magnesium come from massive stars. That's why you start with very high value. And type 1a supernova increase iron. So that's why you see this decreasing trend. That's the basic concept of this figure. Some of them may not be aware. Any other questions? Even the basic one is good. If not, can we finish? Yeah, let's thank the speaker again.